जी, स्क्रीन विजिबल है आपको? हेलो।
Yes, sir.
Okay, जी, so today we shall start chapter 7, which is about entropy. Uh, this is the most confusing concept in the field of thermodynamics, but it is very important concept because without this concept, we shall have huge difficulties in thermodynamics too. In Thermo 2, we shall be discussing about uh, the multiple applications of thermodynamics. So, there, the use of this term entropy is quite common. So, now let's try to understand what is meant by entropy, and I would ask you to fully concentrate on this lecture because that is such a confusing and concept of thermodynamics which is very difficult to understand. All right, so this chapter is again mainly covered from the Eunice Angel book, 8th edition. It's not 5th, 8th edition, chapter 7. And of course, some material is taken from other two books also. So, now, what is entropy? In the second law of thermodynamics, which we have studied in chapter 6, we applied this second law of thermodynamics mainly to cycles and cyclic devices like heat engine, which is a cyclic device, refrigerator is a cyclic device. So we studied how to apply second law of thermodynamics to cycles and cyclic devices, and then we introduced two uh, statements of second law of thermodynamics. In this chapter, we shall be applying again the second law of thermodynamics, but to a process, not a cycle. And then we shall introduce this property which is known as entropy. Because the first law of thermodynamics is all about the property which is known as energy and the conservation of energy. So first law was only about energy, and first law was discussing about energy. Right. The second law, the second law will introduce a new property which is known as entropy. Right, entropy. And first law of thermodynamics was all about quantity of energy. Right. The second law of thermodynamics is about the quality, or in other words, the degradation of energy. That degradation of energy is known as one of the ways to define entropy is represents the degradation of energy. In chapter 6, we have discussed about how energy degrades, because when you take heat out of the system and this heat is converted into work, its temperature drops. So as the temperature drops, we can say it is degraded form of energy, because we cannot take any useful output from that degraded part of energy. So second law is actually telling us about the degradation of energy or quality of energy, which we can define in terms of entropy. So now we shall see what is in throughout this chapter. We are actually trying to understand this concept of entropy, right? So it is not a simple definition like energy that we can define entropy in a simple way, that energy is ability to do work, but entropy is quite complicated or complex concept. So one thing is clear, that second law is actually responsible for the introduction of this term entropy. So entropy is very tedious to define and very difficult to give any physical description, right? of this entropy like energy. Energy is quite clear in thermodynamics. We know what is energy, either in the form of heat or in the form of work or in the form of mass. And in mass, there are various types of energies. So it is all about the quantity of energy. All right. Okay. So now we shall uh, study or try to understand this concept of entropy. So this is the first topic of this chapter, and that is known as the inequality of Clausius or Clausius. So now, what is this thing? Now, both are unknown to us so far: the inequality of Clausius and entropy. Uh, what is this inequality of Clausius? That is given by this term del q by t cyclic integral, that is known as cyclic integral of del q by t is less than or equal to zero. That is actually derived from second law of thermodynamics, but now let's try to understand this expression, what this expression means. For that, we have to see, we have to go back to that example. What is that? That is a heat engine, which is taking heat from a high temperature source, and it is converting it, a part of it is converted into useful work, and the rest is rejected to the sink. So whether it is an ideal heat engine or non-ideal heat engine, the heat has to be rejected to the sink. That is what we have learned in chapter 6. So first of all, let's consider that this heat engine is a reversible heat engine. So here the work which we are getting here in this subscript, it is written, it is irreversible. So a reversible heat engine is the one which will give us the maximum efficiency, or in other words, if it is a heat engine, it is giving us the maximum possible work output. So for a reversible heat engine, here what we are trying to define the cyclic integral of heat transfer. In this heat engine, all the heat transfers which are taking place in that cycle, sum of all the heats which are entering or leaving is greater than zero. So let's try to understand. Here, heat transfer is QH and heat rejected is QL. Now, question is, which one is bigger, QH or QL? What you say? This is a heat engine in which heat is transferred from a high temperature source. A part of it is converted into work. The rest is rejected. So, which heat is bigger in magnitude, QH or of course QH? So the cyclic integral of these heat transfers for this cycle, only heat transfers. So if we sum all the heat transfers in this cycle, so this is the heat transfer to the system, and that is the heat transfer out of the system. So that's why it comes with the negative sign. And this is clear. QH is always greater than QL. So that's why this term, cyclic integral of heat transfer, QH minus QL, will always be greater than zero, because QH is greater than QL. Now let's see another term, that is not heat transfer, it is heat transfer divided by temperature. So del Q by T. So all the heats which are entering, but at what temperature? It is QH, heat from a high temperature source. Now if we divide this, its heat transfer with its temperature. Similarly here, QL divided by TL. Now this term is exactly equal to zero. Why? Because in chapter 6 we learned that for a reversible cycle, only for a reversible cycle, QH by QL is equal to TH by TL. This ratio is exactly same only for a reversible heat engine. We didn't prove it, but we shall prove it in chapter 8, this expression. But that is true only for a reversible heat engine. So here you can write this equation as QH by TH is equal to QL by TL. So both are exactly equal. That's why this expression is exactly equal to zero from here, right? Which is derived from this expression only for a reversible heat engine. So this term del Q by T is equal to QH by TH minus QL by TL. Again, the cyclic integrals of del Q by T, which are taking place in this heat engine. Right. So this is also now correct or clear that QH by TH minus QL by TL is equal to zero. Now, if this TH approaches TL, right? If TH, the difference between TH and TL approaches to zero, then what will be the work output? If TH or TL का जो difference है, that is negligibly small, it is approaching to zero, will there be any work output or not?
No, sir.
No. So in that case, QH minus QL will be approaching to zero. The cyclic integral of del Q, we have said that it is always greater than zero. But if TH approaches TL, then the cyclic integral of del Q will be equal to zero. Right. So overall, we can say for all reversible heat engines, this cyclic integral of heat transfer will always be greater than zero. But at maximum, it may approach to zero if TH is approaching to TL. So that is the conclusion. Similarly, but even if TH is approaching to TL, this term will always be equal to zero. Whether TH is greater than TL or TH is approaching TL, this term will always be equal to zero. So overall, for all reversible heat engines, these are the expressions which will always be true, that the cyclic integral of heat transfer is greater than or equal to zero, and cyclic integral of del Q by T is exactly equal to zero. Now, let's discuss an irreversible heat engine or irreversible cycle. So now for an irreversible cycle heat engine operating between the same TH and TL as for the case of reversible heat engine. Now, then what is the difference between a reversible and irreversible heat engine operating between the same TH and TL? This is the difference. The net work output from an irreversible heat engine will be less than the work output from a reversible heat engine, which is operating between same TH and TL. So hopefully this is clear. Same TH, same TL, but now this heat engine is not reversible. It is irreversible. Then the work of irreversible heat engine will always be less than the work output of a reversible heat engine. This is reversible, but if it is irreversible, then the work output will drop for the same QH and for the same TH. In other words, we also know that we can represent this work transfer as QH minus QL. Right? If we apply the first law of thermodynamics on this whole system, that is the energy entering, these are the two energies which are leaving. So we can write W as QH minus QL. So in other words, we can say this work output of an irreversible heat engine is equal to QH minus QL of irreversible. Because difference is here, whether it is reversible heat engine or irreversible heat engine. For the same TH and QH, difference is here. In a reversible, we will get more W and less QL. For an irreversible heat engine, we will get less W. So it means this loss or the rejected heat will be more. So here, QW irreversible simply means QH minus QL irreversible. is actually less than QH minus QL of a reversible heat. QH is same, whether it is reversible or irreversible, right? So this equation hopefully is clear. So in other words, we are saying that the heat rejected to a sink in an irreversible heat engine will always be greater than the heat rejected to the same low temperature sinks for a reversible heat engine, right? So that is also, that is that we, this implies that this QL of irreversible will always be greater than the QL of reversible heat engine. All right, so far I think this is clear. So cyclic integral of del Q is equal to, in this case, for an irreversible heat engine, QH minus QL irreversible is again always greater than zero, because although QL for our irreversible heat engine is greater than QL for reversible heat engine, but still it is less than QH. Whether it is reversible or irreversible, only a part of this QH will be converted into W. The rest is rejected. So this QH minus QL for an irreversible heat engine will also be greater than zero, just like in reversible heat engine. So now you can see कि मैंने आपको चैप्टर 6 में, अगर आपने मेरे recorded lectures गौर से सुने, I told you the concept of reversible and irreversible is very important to understand this chapter. और अब आप देख लें, जब से मैंने एंट्रोपी स्टार्ट की, मैं कंटिन्यूसली रिवर्सिबल इरिवर्सिबल रिवर्सिबल इरिवर्सिबल की टर्म्स यूज कर रहा हूँ. सो इफ यू आर नॉट क्लियर, go to chapter 6 and listen again or read again about the difference between reversible and irreversible. So this term, which was greater than zero for reversible heat engine, this term is also greater than zero for an irreversible heat engine. But where is the difference? Difference is here. Now, what is this term? Del Q by T. So QH by TH minus QL for an irreversible heat engine divided by TL. For the case of a reversible heat engine, that was equal to zero, right? But here, in case of irreversible heat engine, it is less than zero. Why it is less than zero? Because this QL irreversible, because before, when it was a reversible heat engine, it was QLR, but now QL reversible. But now this term is replaced with this term, which is greater than QL irreversible. So that this term is greater. In case of reversible heat engine, control. For the case of reversible heat engine, this QH by TH was exactly equal to QL by TL. But now this term, for an irreversible heat engine, now this is QL irreversible, and this term is greater than this term. Right? This QL irreversible is greater than this term. So which makes this whole term greater than this term. So this term becomes greater than QH by TH. Because when it was reversible, QL by TL was exactly equal to QH by TH. But now for an irreversible heat engine, the same reversible, this QL reversible is replaced with QL irreversible, which is greater than this QL reversible. So that makes this term greater than this term. So when you subtract this term from this one, it will be a negative number. That's why it is less than zero for an irreversible heat engine, right? Because QL irreversible is greater than QL reversible. So what are the conclusions? For an irreversible heat engine, the del Q will be equal to zero. Del Q may approach to zero as this work output approaching to zero, right? Or TH is approaching to TL, then del Q may approach to zero. Otherwise, del Q will always be greater than zero. Second, this one, this term will always be less than 0 because this term involves this QL irreversible, which is greater than QL of reversible. So this term will always be greater than this term. So that's why it will always be a negative term. So overall, we can say for all irreversible heat engine cycles, del Q, the cyclic integral of only heat transfers, is greater than or equal to 0. Right? Equal to 0 कब होगा when TH approaches to TL, or when, which means W, work output, is approaching to 0. But this term, the second term, will always be less than 0 because of this, which we have just discussed. Right? Any questions so far? Maybe you're not understanding why we are studying this. It will take some time. Why there is a need to study this LQ by T term, right? But so far, whatever we have discussed, if something is not clear, then ask. If you have clear concept of reversible versus irreversible, then it is clear. Hopefully, it should be clear. So that is called inequality of Clausius. This del Q by T term, which we have introduced, it is always less than or equal to 0. Equal to 0 कब होगा? When it is a reversible heat engine. For an irreversible heat engine, it will be less than 0. It can never be greater than 0. Can never be. That is not possible. If this term is greater than 0, that process or that system is impossible. Right? In other words, this is the expression, mathematical expression of second law of thermodynamics. In other words, this is actually second law of thermodynamics. It's mathematical expression. First law क्या था? E in is equal to E out simply, right? फिर इसके जो दो तीन different forms हैं, we have already discussed. That is first law. The mathematical, simple mathematical expression of first law. But the mathematical expression of second law is this one. What this mean? If del Q by T is equal to 0, then it is a reversible process or a reversible cycle. If this term del Q by T is less than 0, then it is an irreversible cycle. If this del Q by T is greater than 0, such process is impossible. That is not possible, right? Or impossible system or impossible process. That is what second law is saying. Now let's discuss this term in more detail. So far we have derived, we have said that this del Q by T is a term which should be less than 0 if it is an irreversible cycle, and it will be exactly equal to 0 if it is a reversible cycle. We are talking about so far cycles, right? So let's see one example, one practical example, and let's apply this to this system. What is this practical system which we are already studying from lecture 1, boiler, turbine, condenser, and a pump. So that is a steam power plant, right? And some data is taken from this plant. So here is point 1. The saturated liquid fluid is entering as saturated liquid at this pressure into the boiler, leaving at this condition or at this state, leaving the turbine at this state, and leaving the condenser at this state. Right. So these are the data points which are taken from that plant. Right. Now we shall apply this Clausius inequality to this plant. And if this del Q by T comes, if it is an actual or real plant means it is an irreversible cycle. This data is taken from an irreversible or actual cycle or actual steam power plant. So now we shall apply this term del Q by T, cyclic integral of del Q by T on this cycle. And this will come out to be less than 0. If it is equal to zero, it means this is reversible heat engine, which is not possible because there is nothing in this universe which is totally reversible. There is no such process because we cannot avoid any all the losses which occurs or all the irreversibilities. And if it is greater than zero, if we apply this del Q by T on this steam power plant and it comes out that del Q by T is greater than zero, then this process or this heat engine is impossible to construct. It will never uh, deviate, or it will never it will never deviate this expression, right? If it is a real process. So now let's apply del Q by T on this cycle. So cyclic integral of del Q by T. So heat is transferred in the boiler or in the condenser. There is no heat transfer in the turbine or pump, although there are some heat transfers, but we are neglecting those small heat transfers from the turbine to the surrounding or from the surrounding to the pump. So surrounding से जो heat transfer हो रही है, that is only occurring in the boiler or in the condenser. So cyclic इस पूरे cycle में कौन कौन सी heat transfer है? Del Q in the boiler and del Q in the condenser. But now we are also dividing this term, this del Q, with the corresponding temperature of the boiler and the corresponding temperature in the condenser or the cold sink. So that is this equation. Now we shall actually calculate this del Q in the boiler and del Q in the condenser. And let's see what is temperature and what is temperature of the condenser and what is temperature of the boiler from this given data. What is the given data? In the boiler, steam is entering as saturated liquid at this pressure. And it is leaving still as saturated vapor at the same pressure. And it leaves the turbine at 90% quality, it means within the dome, and pressure is reduced from 0.7 megapascal to 15 kilopascal. Now it enters at this state into the condenser and leaves, because in condenser is also a heat transfer process, so pressure remains same. And here quality drops from 90% to 10%, right? Because here the heat is rejected and some of the vapor is converted into liquid, but all of the vapor is not converted into liquid, right? That's why the quality is not zero, it is 10%. So now we can find out, we can now put those values of Q's and T's in this equation. So let's, because now here heat is transferred at one constant temperature in the boiler. So this T is constant, 1 over T1, 1 to 2 del Q, plus here during condensation, heat temperature is also fixed because it's also a phase change process. So that's why this T3 is fixed, and 3 to 4, this is del Q. So that is written like here. Heat transfer 1 to 2 divided by T1 plus heat transfer 3 to 4 divided by T3. So now we need to solve this equation. So what is 1Q2? 1Q2 heat transfer in the boiler is simply the enthalpy change, H2 minus H1. That is the equation for boiler. Heat transfer in the boiler is simply given by H2 minus H1, and heat transfer in the condenser is simply given by H4 minus H3 final minus initial H4 minus H3. Here is it is H2 minus H1. So we can see from the table the corresponding values of H1 and H2, and that comes out to be 2066. Similarly, H4 and H3 again from the table and mixture region equation. These are the enthalpies which we have calculated. And at this pressure, this is the saturation temperature. At this pressure of 0.7 megapascal, because it is saturated liquid, saturated vapor, throughout saturated, and it's a boiling process, pressure is constant, so temperature boiling temperature is also constant, and that is 164.97. Similarly, here during condensation, again a phase change process, pressure is constant, which is 15 kilopascal, and at this 15 kilopascal, we can see from table what is the saturation temperature, right? So all the enthalpy differences in the boiler and enthalpy difference in the condenser are calculated, which are actually representing this heat transfer. So let's consider the case of 1 kilogram of a substance. So now by putting values in this equation, this is the heat transfer in the boiler, 1Q2, just this one. Similarly, 3Q4, this one, H4 minus H3. So by putting values, because this term comes out to be a negative number, right? Because H3 minus H4 is less than H3. Because here heat is rejected by the condenser. When heat is rejected in the condenser, the enthalpy will drop. So this H4 will be less than H3 because energy is taken out of that substance, which is steam. Okay. So now by putting values, this del Q by T comes out to be a negative number, right? Del Q by T, this expression, which we have introduced in this chapter, this comes out to be a negative number. So negative number, when del Q by T, cyclic integral of del Q by T is less than 0, the cycle is irreversible and possible. If this del Q by T, which we have already said that if the cyclic integral of this term is equal to 0, the cycle is reversible. If this term comes out to be a positive number, greater than 0, if the cyclic integral of del Q by T is greater than 0, the cycle is impossible because it violates the second law of thermodynamics. So we can check or we can apply this del Q by T, cyclic integral of del Q by T expression on any cyclic process. And it should, if it is a real cycle and if it is definitely occurring or taking place in reality, then this term will always be a negative number. This term cannot be a positive number. If we design such cycle which gives this del Q by T greater than 0, then this process will not occur in reality. This process is impossible to, or this cycle is impossible to operate in reality. So, जो आपकी क्लाशियस और क्लाशियस स्टेटमेंट थी और सेकंड वाज केल्विन प्लैंक स्टेटमेंट, उन दोनों स्टेटमेंट्स का मतलब एक्चुअली यही है कि फॉर बोथ ऑफ दोज स्टेटमेंट्स आर एक्चुअली टेलिंग दिस थिंग, एंड दिस थिंग इज नॉट ओनली valid for heat engine but also for refrigeration cycle. If you apply this del Q by T, cyclic integral of del Q by T on a refrigeration cycle, it will again comes out to be a negative number if it is a real refrigerator. Maximum if it is a Carnot refrigerator or if it is a Carnot heat engine, only then this term del Q by T will be equal to 0. Okay, so this term which we have defined, this term is actually named as entropy. This term del Q by T, it is named as entropy. Okay, so that what is this term? This is heat energy divided by temperature. So heat energy divided by temperature, this term is called or is named as entropy. Okay, so let's further discuss this del Q by T. So entropy, just like enthalpy, just like energy, just like any other thermodynamic property, it is also a property of a system. Let's prove it. Okay, entropy is also a property of a system. It is not a path function. Property is not a path function. Properties are point functions like internal energy, enthalpy, energy, capital this E is not property. but small e is a property. When you divide this extensive property with the mass, it becomes intensive, right? So this E or small h or small u or temperature, pressure, all these are thermodynamic properties. Now we are saying, and what is the property of property? That those are independent of path. Those are only dependent upon endpoints, initial and final state. Okay. So entropy is also a property. What is entropy? We are saying that this term is entropy. Del Q by T is entropy, right? But still, we would like to know what is the real meaning of this thing. So let's continue our discussion so that we can have some idea what is this term del Q by T. So let's prove it whether this term is also entropy. So here we shall prove it in a similar way, which we used in chapter 2. अगर आप chapter 2 में देखें, so we also proved similar thing for this thing. Del Q minus del W is equal to delta U, internal energy, or delta E, sorry, delta E. And we said this delta E is a property of a system. And to prove this thing, whether it is a property, we used a similar procedure in chapter 2, which we will now use here. So here what we see, there is a system um, which is actually a control mass undergoing a reversible process. What is the reversible process? From state 1 to state 2 by following this path A, and then it completes the cycle by following path B, 2 to 1. So 1 to 2 and 2 to 1 makes a cycle. And if it is a reversible cycle, for a reversible cycle, we know that for a reversible cycle, this is something we have discussed or derived from Clausius inequality, that for a reversible cycle, that is true. That will always be equal to 0. So in other words, for process 1 to 2 del Q by T by following path A plus the same del Q by T for path 2 to 1 for process 2 to 1 by following path B is equal to 0, right? Similarly, now let's see another cycle. Another cycle is that it is following this path C from 1 to 2, a different path from A, and then it completes the cycle by following the same path B. Now this C and B from 1 to 2 and 2 to 1 is another reversible cycle. So we can write the same equation for this new reversible cycle. Right, del Q by T, 1 to 2 for path C and 2 to 1. So all the heat transfers during this path and all the heat transfers during this path are equal, right? Sorry, not equal, their summation is equal to 0 for a reversible cycle. Now, if we subtract this equation from this equation, then this term will cancel. So subtract this equation from this equation. So what we will get, this term will cancel and this will be equal to this one, right? By subtracting these two equations. So what we get here, del Q by T for path A from 1 to 2 and del Q by T for path C, because these are two different paths, right? But this del Q by T term for A and del Q by T term for C for the same processes, for the same process path 1 to 2 are exactly equal. So it means this term del Q by T is independent of path, whether it follows this path or it follows this path. Both are equal. So those are independent of path. So this del Q by T is the same whether it is reversible for all the reversible paths between 1 and 2. So it means this quantity del Q by T is not dependent upon path, and it is only a function of end states. Only the end states. They are only dependent upon end state, but not the path. So is an this is a new thermodynamic property which is named as entropy. So entropy is also a thermodynamic property because it is independent of path. That is what we want to explain, or we wanted to prove here. So now this term entropy was actually discovered by this person Clausius in 1865. Entropy, which is a property of a system. So how it is defined? The we del Q by T, right? And the symbol which is used in thermodynamics, that is S. ds is equal to del Q by T. Units are clear. Here it is energy, joules, divided by temperature, absolute temperature, single T, so it's always absolute temperature. So kilojoules per Kelvin is the entropy change during any process, del Q by T. And that is for an internally irreversible process, right? So that is an extensive property because it is dependent upon, because Q is dependent upon mass. So when Q is dependent upon mass, so S is also dependent upon mass. So that's why it is an extensive property. And we can also write it in terms of intensive. If we divide it with mass, this term, so this will become d into small s. We use small s for specific properties, or in because when you divide it with mass, it becomes intensive or specific. So this will be del small q divided by small q. So that is called change in entropy. And how we can find this change in entropy for any process from 1 to 2. So we have to integrate this equation. Just like if you remember, work done was given by this PDV product. PDV product between 1 to 2. 1 to 2. Similarly, here to find out this entropy change, we need to integrate this equation del Q by T from process 1 to 2. So just like enthalpy or internal energy, if you remember what was dH, change in enthalpy, that was given by Cp into T2 minus T1, Cp delta T. Similarly, dH, du, change in internal energy, was Cv into delta T or T2 minus T1. And how to calculate these enthalpies, if you remember, we said at 0 Kelvin, we said that enthalpy HU is 0. That is 0. At 1 Kelvin, we calculate enthalpy from here, right? If we know the Cp of that substance into T2 minus T1. What is T2? 1. What is T1? 0. So we can calculate change in enthalpy at this 1 Kelvin, and we can write its value here, 1.2, for example. And this is, for example, internal energy, which is 1.1. And so on. Then similarly for 2 Kelvin, we can integrate this equation from 0 to 2 Kelvin, or from 1 to 2 Kelvin. So T2 minus T1. That's how we can calculate enthalpies and internal energy at different temperatures. But we start from here. We take some value, we take some reference at which we assume enthalpy and internal energy as energies are 0. And then we start calculating all these enthalpies and internal energies using these equations for change in enthalpy or change in internal energy between 2 points. Similarly, here we can also write entropy. So we can calculate entropy in a similar manner as this H and U. Here we shall say that entropy is 0 at 0 Kelvin. So it means this term del Q by T is 0 because there is no heat transfer, is 0. And then we start calculating entropies at higher temperatures by evaluating this integral, because here del Q is mc delta T, change in temperature from 0 to 1 Kelvin divided by the temperature at which in between 0 to 1. So it means we have to integrate from 0 Kelvin to 1 Kelvin. Right. So that's how we can calculate entropies of any substance at different temperature at 0 Kelvin, 1 Kelvin, 2 Kelvin by solving this equation or by integrating this equation between any two temperature changes, but starting from a reference temperature at which everything is 0, and that is 0 Kelvin in most of the cases. So entropy is calculated just like enthalpy and internal energy, but the equation is del Q by T. Here it is simply del Q, Cp delta T or Cv delta T. Here it is Cp delta T divided by T, if it is a constant pressure process, or it is Cv delta T divided by temperature, and you have to integrate. So that's how the entropy values are calculated, and those are tabulated in those saturated tables. Are you with me?
Yes, sir.
All right. So still वी आर नॉट श्योर कि ये एंट्रोपी है क्या. ठीक है, इसको अभी डिफाइन अभी हम कोशिश करेंगे विद द पैसेज ऑफ टाइम व्हाट define this term correctly. Till then, just understand what we are learning on a particular slide. Right. So entropy is something which is dependent upon heat. But here, what we do, we divide this heat with temperature, and we named it as entropy. ठीक है. फिलहाल बस हमने अभी इतना ही इसको समझा है. So let's continue further. और हमने what we have said that it is an extensive property. It is dependent upon mass. ठीक, चेंज इन एंट्रोपी कैसे फाइंड करना मैंने आपको एक्सप्लेन कर दिया. फॉर एग्जांपल हियर यू सी ऑन टीएस डायग्राम, this is a reversible process which we can trace, and that is an irreversible process which we cannot trace. We do not know the path taken by an irreversible process between 1 and 2. But the entropy is independent of path, so that's why the entropy change will always be 0.7 minus 0.3. Whether it is a reversible process or it is an irreversible process, this entropy change will always be same. So this equation enables us to find out the entropy change along a reversible path, right? So once you calculate this entropy change using reversible path, then it will be same whether it is an irreversible, because this change in entropy is independent of path, and we calculate this change in entropy by assuming a reversible path which is traceable and whose equation we can be derived once the path is known. So then we can find out the entropy change, and this entropy change will be same whether it is reversible or irreversible, because this entropy change is independent of path. So for example here, for an isothermal heat transfer process or internally reversible, ये भी हमने chapter 6 में पढ़ा था, isothermal heat transfer, when the heat is transferred at a constant temperature, for example during boiling or during condensation, at least on the system side, the temperature is not changing. So that is an isothermal heat transfer process. So for an isothermal heat transfer process, we can find out the change in entropy using this equation, but here T is constant, right? Because isothermal. That's why you can calculate the entropy change using this equation by evaluating this equation, right? So that will be Q divided by T naught for an isothermal process. The integral is easy to evaluate because here T is constant. At a constant temperature, heat is transferred, either absorbed or rejected. So this del Q will be simply Q divided by T naught. That's how the heat transfer uh, at a constant temperature can be used to calculate the entropy. Right. And isothermal heat transfer process is internally reversible, not externally, because heat is transferred from some external source whose temperature is changing. But internally, there is something which is boiling or condensing, so that's why there is no temperature change. Temperature is constant. Okay. Now the next topic is very important and may not be easy to understand. So try to focus and concentrate fully because it will take some time to understand this concept of entropy. I'm telling you again and again. Till the end of this chapter, we will be in a position to understand this concept. Now, what is this? The increase of entropy principle. So what you see here on this figure, there is a cycle following this path 1 to 2, which may be reversible or it could be irreversible. This path 1 to 2. And then 2 to 1 is definitely irreversible, at least internally reversible. So that is a cycle consisting of two processes, 1 to 2, which is irreversible or it could be reversible. Right. So here we have both possibilities. Then the second process or the second path is the reverse path is totally irreversible. Right. So 1 to 2 and 2 to 1. These are the two processes which completes a cycle. So, and we know this is the Clausius inequality for a cyclic integral of del q by t is either less than or equal to zero. Equal to zero if it is a reversible cycle. If this complete cycle is totally reversible, यानी दोनों processes अगर reversible है, then del q by t will be equal to zero. If one of the process or two or both processes are irreversible, then del q by t will always be less than zero, which we have already discussed in the topic of Clausius inequality. So this is the equation which we will use and we will apply to this cycle. So here for process 1 to 2 del q by t plus process 2 to 1 del q by t. During this process, whatever heat is transferred and at whatever temperature is written here, plus for the reverse process 2 to 1 or the return process. But this process is definitely reversible. This process may be reversible or may not be reversible. Okay, this process which is reversible, whose path is known, ये जो path है 2 to 1 which is reversible, 2 to 1. This is 1 to 2 and then 2 to 1. This path is reversible path, and that's why we can trace this path and we can evaluate this entropy because we know the path, we know its equation, and we can put this equation here and we can solve it. Right. So, for example, after solving, we can calculate this change in entropy. What is this change? S1 minus S2. Final minus initial, because this del q by t represents change in entropy and it is a reversible path which we can trace and which we can solve, right? Whose equation can be solved. We know how this q is changing with respect to temperature because the equation of this path is known, can be known if it is fully reversible. So that's why it is written as, what is this change from 2 to 1? Final minus initial, means S1 minus S2. So this equation is written this like this. We don't know about this path. It could be reversible, it could be irreversible, right? So that's why we cannot evaluate if it is irreversible. That is written like this. Now, BC equation may now, if we take these two terms on the other side of this expression, so this will become S2 minus S1. So now this equation transforms to this form. So now this is taken on the other side, so it becomes S2 minus S1, which is greater than or equal to del q by t, right? S2 minus S1. What is S2 minus S1? S2 minus S1 representing this path, the entropy change of this path, S2 final minus initial, right? So what this expression is saying that S2 minus S1 is greater than or equal to this term, this del q by t for path 1 to 2, and that could be reversible or it could be irreversible. If it is a reversible path 1 to 2, then S2 minus S1 is exactly equal to del q by t, right? If it is reversible. If it is irreversible, then this change S2 minus S1 will be greater than del q by t. Now, this is important to understand. For an irreversible path, if this path is irreversible, 1 to 2, then this entropy change is greater than this term, del q by t. What this mean? For an irreversible path, uh, during this process, some heat is transferred, some process took place, some heat is transferred to the system or out of the system, due to which this change has taken place. यानी 1 से लेके 2 तक आपका substance गया, right? And during this process, some heat was transferred, or some work was done, or something was uh, occurred, and that's why this change took place, right, from 1 to 2. But for an irreversible process, whatever heat was transferred here, for example, there was some heat transfer, all of this heat which is transferred during this process is not fully utilized. Some of it is lost. Some of it was lost. Or for example, during this process, some work was done, जिसकी वजह से ये change आई 1 से 2. But whatever work which we have supplied from the surroundings, some of it was lost. Loss simply means not destroyed. Some of this energy was converted into such a form which is irrecoverable. There are some irrecoverable losses during that actual process. What is that actual process? Irreversible process. So it means कि for example अब इस equation में देखें, इस equation में ये जो energy transfer हुई है during this process, all of it was not, some of it was used to change this state from 1 to 2, and some of it was lost. So actual energy which was used here was more than this Q, because this Q brought this change from 1 to 2. But there is some energy which was not used here, that was lost. That's why entropy change during this process, during an irreversible process, is greater than this term, because this term has actually made this change possible from 1 to 2. But all of it was not used, some of it was lost. So this lost plus this Q which made this change is actually this term, which represents the total change in entropy, which is greater than del Q by T. If there is no loss, if it is a fully reversible process, it means no losses at all. It means whatever energy was transferred was fully used to change this state. So that's why S2 minus S1 is exactly equal to del Q by T for a reversible process. But for an irreversible process, S2 minus S1 is greater than this term, because this is the energy which made this change, but there is some extra energy which was lost or which was converted into some irrecoverable form, right? That irrecoverable form of energy, or that lost term during that process, is actually creating entropy. That is the source of entropy. So that's why this entropy change is equal to this term if it is fully reversible. So 2 to 1 है, that is fully reversible. Then this term, or ये जो process of 1 to 2, if it is fully reversible, then this delta S is exactly equal to del Q by T. But if it is irreversible, then this delta S will be greater than del Q by T. जी, कोई क्वेश्चन है तो पूछें. This concept is very tricky, but I tried my best to deliver it in the most possible way. लेकिन book में कोई इससे ज़्यादा explanation है नहीं, बहुत to the point explanation है. If you couldn't understand anything, just tell me again so that I can repeat. ये जो expression है, for an irreversible process, this entropy change is greater than this term. This is entropy change, and that is called entropy transfer. Actual energy जो transfer हुई जिसने ये change create की, but during that energy transfer, some of some was lost or some was converted into an irrecoverable form. So that's why the actual energy which is transferred was more than this one. So reversible process में चूंकि there are absolutely no losses, so this entropy change is exactly equal to del Q by T, right? So ds, this is, we are saying that entropy change during a process is always greater than or equal to del Q by T. Equality means internally reversible process, at least internally irreversible process, and inequality means greater than, this term means irreversible process, right? So entropy change of a closed system during an irreversible process, this entropy change during any irreversible process is always greater than this term, the integral of this del Q by T. So this term del Q by, sorry, this term del S, delta S, or entropy change, this is known as entropy change, and this term on this side, on the right hand side, is known as entropy transfer with heat. That is the energy which is actually transferred, and but there are some losses due to which this entropy changes more during this process, and that is the actually energy which was transferred with heat. So entropy change of a closed system during an irreversible process is always greater than the entropy transfer. The entropy change or an irreversible process is always greater than the entropy transfer. Gee, any question? That is the most difficult chapter or the confusing chapter of thermodynamics. No questions? Okay, there are 30 people. Okay, so it means you will be waiting for the recording. So, मैं फिर आगे चलता हूँ. So whatever we have discussed so far, the overall conclusion is that during every process, and every process in reality is irreversible due to the presence of irreversibility. So during every irreversible process, some entropy is generated, because here we are saying delta S is Ts is greater than this term, is generated or created during an irreversible process, because during every irreversible process there are losses, and those losses represents the irrecoverable form of energy. So wo jo irrecoverable form of energy hai, that is actually known as entropy, right? जब आपने वर्क कोई भी compression process हो रहा है, expansion process हो रहा है, there is a work transfer, but all of this work transfer is not converted into heat. Some of it is converted in the form of losses, and that loss is actually representing the change or rise in entropy. So some entropy is generated or created during any irreversible process. Heat transfer process be irreversible. You cannot reverse it. Whenever you will reverse, there will be permanent changes in the surroundings. In chapter 6 में reversible versus irreversible, उसको दोबारा go through करें, अगर वो clear हो जाएगा concept, only then you will be able to understand this concept of entropy. So ये जो generation हो रही है, entropy generate हो रही है, this generation is only due to the presence of irreversibilities. Or what are the causes of irreversibilities, which we have discussed in chapter 6. Heat transfer is an irreversible process. Friction, the presence of friction is makes the process irreversible. And there are other processes, but we are mainly concerned with the friction and the heat transfer. Okay, so it means if we are saying that delta S is greater than del Q by T, right? have just said, for an irreversible process, delta S, change in entropy is greater than del Q by T. So if we say that this delta S is equal to delta Q by T, by adding this term S, the entropy which is generated during this process. So we can make this term equal, but with the addition of this. So change in entropy during any process is equal to del Q by T plus some entropy which is generated, right? And this S generated is always a positive quantity. This cannot be a negative. For a reversible process, this could be zero, because for a reversible process, this delta S is exactly equal to del Q by T, means no entropy is generated. But for an irreversible process, always there is some entropy which is generated, which means it is a positive quantity. It cannot be negative. So this S generated negative is impossible. That is not possible. Right? Impossible process. So this S generated will always be a positive quantity. Maximum it could be, or minimum it could be zero if it is a fully reversible process, but this term negative cannot be possible. Right? So for example, there is an isolated system. For example, our universe, this is our universe, right? And this universe has certain boundary. We don't know what is, if there is any boundary of that universe, but if we just assume that this universe has certain boundary, across this boundary, no energy is crossing in the form of heat. This Q is zero if this universe has some boundaries. So if we apply this equation to this universe, across which there is no energy transfer, no heat, no work transfer, it means that we are talking about an isolated system जिसके across ना कोई energy transfer नहीं हो रही, कोई mass transfer नहीं हो रहा. So, and what is the example of an isolated system? It is a universe, for example. So for an isolated system, Q is zero because there is no heat transfer. So for an isolated system, Q is exactly zero, right? There is no energy which is transferred, right? So now in this equation, इसी equation को अगर हम इस isolated system पे apply करें, in isolated system some process took place, but there is no energy transfer, there is no heat transfer. So this equation turns out to be that delta S of this isolated system is equal to S generated. Although there is no heat transfer in this system, in this isolated system, right? So it means this term will be zero because del Q is zero. So then it says that the change in entropy of that system is equal to S generated. It means for an isolated system, entropy is being generated. इस सिस्टम में सराउंडिंग्स के साथ कोई हीट ट्रांसफर नहीं हो रही, बट विद इन द सिस्टम देयर आर irreversibilities. Within the system, there are processes occurring. There is systems and surroundings within this big system. And all those systems are creating entropy. So entropy is termed as the measure of disorder of a system, right? So this term, entropy, is continuously increasing for an irreversible process. So, so this universe, which is an isolated system, so for isolated system, although there is no heat transfer, but what is the term which is remaining? S generated. So it means for an isolated system, this delta S, change in entropy, an isolated system is always greater than or equal to zero. If everything within this isolated system is fully reversible, then this term will be zero. Otherwise, even for an isolated system, which is our universe, it is always greater than zero. So it means the entropy. And what is entropy? Uh, the best way to remember entropy is just remember that whenever there is a process, whether it's a heat transfer or work transfer, कोई भी process है, wherever there is energy transfer, during that energy transfer, some of the energy is converted into loss. And what is loss? The irrecoverable form of energy. So that irrecoverable form of energy is just chaos because that is irrecoverable. It is not destroyed, it is still there in our surroundings or in our system, but that cannot be useful. It cannot be converted into some useful form. So that irrecoverable or irreversible form of energy is actually a measure of entropy. That is one way to understand. So when we are saying the entropy of an isolated system is continuously increasing, delta S, and S generated is always a positive quantity. So, right. So delta S of this isolated system is always greater than or equal to zero. So it means S is continuously generated. That irrecoverable form of energy is continuously increasing, increasing, increasing. That is called the increase of entropy principle. Uh, what was that which we have just derived, or that change in entropy is always greater than this term. Maximum, it could be equal to this term. So this change in entropy is greater than this term means it is always a positive quantity, right? And that's why the entropy of this universe or of any process which takes place is actually increasing. And what is the increase in entropy means? Increase in disorder, increase in the irrecoverable form of energy, increase in the loss of energy, right? Okay, I stop here. ये हमने 10 slides cover की हैं. Try to go through those slides again.